Welcome back. In this part of Module 3, we'll be exploring supervised machine learning in detail. As we move into this section of the presentation, we'll dive into the core concepts, algorithms, and real-world applications that make supervised learning a cornerstone of modern artificial intelligence. We'll examine how machines learn from labeled data, analyze different types of supervised learning algorithms, and evaluate their performance through established metrics. By the end, you'll have a solid understanding of how supervised learning powers many of the AI systems we interact with daily. Understanding supervised learning. Definition. Supervised learning is a machine learning approach where algorithms learn from labeled training data. The model learns the mapping function from input variables to output variables, allowing it to make predictions on new, unseen data. Key components. The process requires a labeled dataset, a model architecture, a loss function to measure prediction errors, and an optimization algorithm to minimize errors during training. Learning process. During training, the model makes predictions, compares them to actual labels, calculates error, and adjusts its parameters to improve. This cycle repeats until performance plateaus or a stopping criterion is reached. Types of supervised learning problems. Regression. Regression models predict continuous numerical values. The output exists on a spectrum rather than in discrete categories. House price prediction based on features. Stock market forecasting. Temperature prediction. Age estimation from photographs. Classification. Classification models predict categorical labels, assigning inputs to one of several predefined classes. Email spam detection. Medical diagnosis of diseases. Sentiment analysis of text. Image recognition. Real-world applications. Email filtering. Classification algorithms analyze email content and metadata to automatically separate spam from legitimate messages, protecting users from phishing attempts and unwanted solicitations. Real estate valuation. Regression models process property features, location data, and market trends to estimate home values, helping buyers, sellers, and lenders make informed decisions. Medical diagnosis. Classification systems analyze patient symptoms, test results, and medical images to assist healthcare professionals in identifying diseases and conditions with greater accuracy. Linear regression, the foundation. Mathematical model. Linear regression models the relationship between variables using a linear equation, y equals beta 0 plus beta 1 times x1, plus beta 2 times x2, and so on, up to beta n times xn, plus epsilon, where beta values are coefficients and epsilon represents error. Parameter estimation. The model finds optimal coefficients by minimizing the sum of squared differences between predicted and actual values, typically using methods like ordinary least squares. Assumptions. Linear regression assumes linearity between variables, independence of errors, homoscedasticity, which means constant error variance, and normally distributed errors. House price prediction example. Data collection. Gather historical housing data including size, location, bedrooms, bathrooms, and sale prices. Feature engineering. Transform raw data into meaningful features, such as normalizing square footage or encoding neighborhoods. Model training. Apply linear regression to learn coefficients that best predict prices from features. Price prediction. Input features of new properties to estimate their market value. Logistic regression, beyond linear models. Sigmoid function. Transforms linear regression output into probability values between 0 and 1. Threshold decision. Probabilities above threshold, typically 0.5, classify as positive class. Log loss. Measures error between predicted probabilities and actual classes. Parameter update. Model adjusts coefficients to minimize log loss through gradient descent. Customer churn prediction. Customer data. Collect demographics, behavior, and engagement. Historical patterns. Analyze usage metrics and account activity. Feature importance. Discover key factors driving customer decisions. Accurate prediction. Identify at-risk customers with 85% plus accuracy. Model evaluation metrics, regression. Mean squared error. MS equals 1 over n times the sum of y sub I minus y hat sub I squared measures the average squared difference between predicted and actual values. Higher penalties for larger errors make it sensitive to outliers. Root mean squared error. RMSE equals square root of MSE returns error in the same units as the target variable, making it more interpretable. For house prices, an RMSE of $50,000 means predictions are off by that amount on average. R squared. R squared equals 1 minus the residual sum of squares divided by the total sum of squares indicates the proportion of variance explained by the model. Values range from 0 to 1, with higher values indicating better fit. Practical evaluation, house price model. $45,320 RMSE, the average prediction error in dollars. 0.82 R squared, the proportion of variance explained by the model. 8.7% mean error, the average percentage deviation. 92% within range, predictions falling within the acceptable error margin. Understanding classification fundamentals. Classification is a supervised learning technique where algorithms learn to assign labels to input data based on patterns learned from labeled training examples. Unlike regression, which predicts continuous values, classification predicts discrete categories or classes. The applications of classification are ubiquitous across industries, detecting fraudulent transactions in banking, categorizing customer sentiment in reviews, diagnosing diseases from medical images, and filtering spam from legitimate emails. Labeled training data. Algorithms learn from historical examples with known outcomes. Pattern recognition. Models identify features that distinguish between classes. Prediction. New data is categorized based on learned patterns. Iterative improvement. Models refine decision boundaries through training. Model evaluation metrics, classification. Accuracy. Proportion of correct predictions among total predictions. Precision. Proportion of true positives among positive predictions. Recall. Proportion of true positives identified from all actual positives. F1 score. Harmonic mean of precision and recall. Evaluating classification performance. Selecting the right performance metrics is crucial for evaluating classification models effectively. While accuracy provides a simple overall measure, it can be misleading in imbalanced datasets where one class significantly outnumbers others. More nuanced metrics like precision, recall, and F1 score offer deeper insights into model performance, especially in domains where false positives or false negatives carry different consequences. For instance, in medical diagnostics, failing to identify a patient who actually has a condition, a false negative, can be more harmful than mistakenly identifying someone as having the condition when they don't, a false positive. The following illustration presents the metrics along with their corresponding formulas and outputs. Practical application, email spam detection. Email spam detection exemplifies classification algorithms in action. By analyzing message characteristics like sender information, content keywords, and structural patterns, models can effectively separate legitimate messages from unwanted spam. Different performance metrics reveal distinct aspects of model effectiveness. Precision reflects the accuracy of spam flagging, while recall indicates the system's ability to catch all actual spam. The F1 score balances these considerations, providing a single metric for overall performance evaluation. 97% accuracy, the proportion of correctly classified emails out of all emails. 92% precision of emails marked as spam, the percentage that are actually spam. 95% recall of all actual spam emails, the percentage correctly identified. 93.5 F1 score, the harmonic mean, providing a balanced performance measure. Decision trees, intuitive classification. Decision trees create a flowchart-like structure where each internal node represents a test on an attribute, each branch represents the outcome of the test, and each leaf node represents a class label. They split the data recursively based on feature values to create homogeneous subsets. Their interpretability makes them invaluable in scenarios requiring transparent decision-making, such as loan approval processes where applicants need to understand why they were approved or rejected.
Feature selection. Algorithm chooses the most informative feature for splitting data. Data splitting. Dataset is divided based on selected feature value. Recursive partitioning. Process repeats on each subset until stopping criteria is met. Leaf assignment. Terminal nodes assigned class labels based on majority class. Random forest classifier, a robust ensemble approach for ML classification.
Random forest is a robust and flexible ensemble algorithm that builds multiple decision trees on random data and feature subsets. It combines their outputs via majority voting, classification, or averaging, regression, to improve accuracy and reduce overfitting. Its reliability, resistance to noise, and minimal tuning needs make it ideal for tasks like medical diagnosis, fraud detection, and customer analytics. How random forest works, the ensemble mechanics. Bootstrap sampling. Random subsets of the original data are selected with replacement, bootstrap samples. Decision tree training. Individual trees are grown using a random subset of features at each split. Feature randomization. At each node, only a subset of features is considered for the split decision. Aggregation. Final prediction combines results from all trees, majority vote for classification. The strength of random forest lies in its diversity through randomness approach. By introducing randomness at both the data level, through bootstrap sampling, and the feature level, by considering only a subset of features at each split, the algorithm creates decorrelated trees that capture different patterns in the data. This ensemble approach makes random forest exceptionally robust against noise and outliers, while providing high-quality predictions across a wide range of datasets without requiring extensive parameter tuning. Evaluation metrics and real-world applications. Evaluation metrics. Confusion matrix visualizes prediction errors. Precision, positive predictive value. Recall, sensitivity to positive cases. F1 score, harmonic mean of precision and recall. ROCAUC models ability to discriminate. Log loss evaluates probability estimates. Real-world applications. Medical diagnosis, detecting diseases from patient data. Fraud detection, identifying suspicious financial transactions. Credit scoring, evaluating loan applicant risk. Customer churn, predicting which customers might leave. Image classification, identifying objects in images. When evaluating random forest classifiers, it's crucial to select appropriate metrics based on your specific use case and class distribution. For imbalanced datasets, metrics like precision, recall, and F1 score typically provide more insight than accuracy alone. Random forest's ability to handle high-dimensional data, capture nonlinear relationships, and provide feature importance rankings makes it particularly valuable in domains where interpretability matters alongside predictive performance, such as healthcare, finance, and customer analytics. K-nearest neighbors, classification by proximity. K-nearest neighbors exemplifies lazy learning. It doesn't build an explicit model during training but instead stores all training examples in memory. When classifying a new instance, KNN identifies the K closest training examples in the feature space and assigns the majority class among these neighbors. The intuitive nature of KNN makes it particularly effective in recommendation systems where similarity metrics drive suggestions. For example, streaming services might recommend movies based on viewing patterns of users with similar tastes. Distance calculation. Compute distances between new point and all training points. Neighbor selection. Select K points with smallest distances. Majority voting. Assign class based on most frequent class among neighbors. Parameter tuning. Optimize K value through cross-validation. Support vector machines. Linear separation. Linear SVMs find the optimal hyperplane that maximizes the margin between classes in the original feature space. This works well when data is linearly separable but struggles with more complex patterns. Kernel trick. The kernel trick implicitly maps data into higher dimensional spaces where linear separation becomes possible. This allows SVMs to capture complex nonlinear relationships without explicitly computing the transformation. Soft margins. Soft margin SVMs introduce a penalty parameter that balances maximizing the margin and minimizing classification errors. This makes the model more robust to noise and outliers in real-world datasets. Support vector machines, optimal boundaries. Support vector machines identify the optimal hyperplane that maximizes the margin between different classes. This sophisticated algorithm excels in high-dimensional spaces and situations with clear margins of separation between classes. The kernel trick, a mathematical transformation that implicitly maps input data to higher dimensional spaces, enables SVMs to handle nonlinear classification tasks. This makes SVMs particularly valuable for complex problems like image recognition and biological sequence classification. Regularization. Balance between margin maximization and classification errors. Kernel functions. Transform data to enable nonlinear classification. Support vectors. Critical points near decision boundary that define the hyperplane. Maximum margin. Find boundary that maximizes distance between classes. Performance comparison of popular machine learning algorithms. The following comparison highlights the performance of linear regression, logistic regression, decision tree, random forest, and support vector machine based on percentage accuracy, training speed, and ease of interpretation. Ensemble methods, collective intelligence. Ensemble methods leverage the wisdom of crowds by combining multiple models to produce more accurate predictions than any individual model. Bagging, a technique also known as bootstrap aggregating, and pasting represent two techniques for creating diverse base models within an ensemble. Random forest, a popular bagging implementation, creates multiple decision trees trained on random subsets of the data with replacement. This approach reduces variance and overfitting while maintaining the interpretability advantages of decision trees. Bagging creates subsets of the original dataset through sampling with replacement, a method known as bootstrap sampling. Reduces model variance. Combats overfitting. Parallel training possible. Pasting creates subsets of the original dataset through sampling without replacement. Ensures data point uniqueness. Promotes model diversity. Effective with large datasets. Aggregation combines predictions through voting, for classification, or averaging, for regression. Smooths individual model errors. Improves stability. Enhances generalization. Neural networks, deep supervised learning. Input processing. Neural networks transform raw input features through an input layer into a format suitable for processing. Each neuron represents a feature and passes information forward with appropriate scaling. Hidden layer computation. Multiple hidden layers process data through weighted connections and nonlinear activation functions. Each layer extracts increasingly abstract representations of the input data, enabling the network to learn complex patterns. Output generation. The output layer produces predictions tailored to the problem type, a single value for regression or class probabilities for classification. The network optimizes weights through backpropagation to minimize a specified loss function. Key takeaways. Supervised learning provides powerful tools for making predictions from labeled data. We've explored foundational algorithms like linear and logistic regression, classification methods, as well as more complex models like SVMs and neural networks. Each algorithm offers unique strengths for different problem types. Proper model evaluation is critical for real-world applications, requiring appropriate metrics for regression and classification tasks. As you continue your machine learning journey, remember that selecting the right algorithm and evaluation approach depends on your specific data characteristics and business requirements. Thank you and next steps. We sincerely appreciate your participation. In the next session, we'll move on to Module 4, which will focus on unsupervised learning. This module will cover important topics such as clustering methods and dimensionality reduction, highlighting their roles in enhancing model efficiency and reliability. To stay updated with our future educational content, we invite you to subscribe, like, share, and continue engaging with our learning resources.